Okay, so we are live. So chapter 22 is on acids, bases, and salts. Section 1 is on acids and bases. We'll cover that today. Next week, we'll have section 2, strength of acids and bases, and then section 3, salts. So the main idea for section 1 is that acids produce hydronium ions or hydrogen ions in solution or in water, and bases produce hydroxide ions. And we'll find that those lead to similar properties for those solutions. And so the essential questions that we want to be able to answer are: what defines an acid or a base? How are common acids and bases used? And how do acids and bases form ions in solution? And so we've previously talked about ionic substances and how they dissociate in solution. So if you take an ionic salt, you put it in water, it's going to dissolve most times. And so acids and bases dissolve in a similar manner. However, when they dissolve, they give the solution new properties. And so these aren't just salt solutions. These are special solutions that yield specific properties. That's what makes them an acid or a base. So some new vocabulary terms for us. We have acid, base, hydronium ion, hydroxide ion, although that might be considered review because we did have hydroxide ion when we were learning about our nomenclature way back when. It was, if you recall, it was one of 2 polyatomic ions that was found on our polyatomic ion sheet that end in IDE, the other one being cyanide. And then we'll learn what an indicator is. And so these are the general acid characteristics. So you want to kind of keep track of what's what in terms of acids versus bases and things that are similarity between the two. For your notes, it might be a good idea to set up, I wouldn't do a Venn diagram because when you do Venn diagrams, there's the double circles with the overlapping in the middle. I wouldn't do one of those because whenever you do that for your notes, you always seem to have too small of a space in the middle. I think you know what I'm talking about. And so I would encourage you to do a triple column chart. So you'll have acids, bases, and in the middle acids and bases. So you'll put properties of acids, properties of bases, and then properties right in the middle. Most of these will be directly written in the slideshow. Some of them I'll provide them verbally. Other ones you'll find in the book. So the first property for acids is that they are generally sour in taste. And so while we don't seek out to taste laboratory grade acids because acids can be extremely toxic and corrosive, we do know that some substances that are found naturally in some of the foods we eat have the property of being sour. So that's how we know acids are sour. And so if you think about some sour substances like citruses, lemons, limes, oranges, maybe not oranges as much, but lemons and limes especially, they are sour because they have a high acidic content. The acid in citruses is called citric acid, named because it's the acid found in citruses, of course. And so that's an example of an acid tasting sour. Another example would be vinegar. Vinegar has a sour taste. And so vinegar is the main component in vinegar is acid. And so it's acetic acid. And so acids have a sour taste. So acids, like I just mentioned, acids are found in citrus fruit. And we'll actually find acids found in soda. Soda has I wouldn't consider soda sour, but soda has a very slight sour taste to it if you think about it. And what that is they add phosphoric acid for the taste of the soda. So that is an acid found in soda. And then by virtue of dissolving carbon dioxide to make the drink carbonated, soda will be it will have carbonic acid as well, because when you dissolve carbon dioxide in soda, it forms carbonic acid. So there's actually 2 different acids in soda: carbonic acid and phosphoric acid. So you probably heard that soda is not good for your teeth. Well, that's why. It's because it has acid in it. So acids, they're known to be highly reactive, and so we've used acids in laboratory before. We did it for our moles lab. We took some zinc and we dissolved it in hydrochloric acid. When we dissolved the hydrochloric acid, it produced hydrogen gas, which we then reacted with oxygen to create a combustion reaction. And so that was an example of a metal reacting with acid to produce hydrogen gas. So a lot of metals will react with acid to produce hydrogen gas. Some metals will not, but a good portion of them do. So yeah, The next thing is that acids react with carbonates. They dissolve carbonates, and when they do that, they form carbon dioxide. The very popular, ever classic volcano reaction, where you might have even done this at some point in your life, or nevertheless you've probably seen it done. When you take acid and vinegar is your acid. When you take vinegar and you combine it with baking soda, it creates this bubbly mess. Well, that's precisely what's happening. Is you have an acid, the vinegar, reacting with a carbonate, the baking soda, to produce carbon dioxide. This reaction also happens with carbonic acid. No, it happens in the Earth's oceans. This is what leads to the acidification of the oceans. So when carbon dioxide dissolves in the water, it creates carbonic acid, and this makes it difficult for calcifying organisms to create their shells, because these organisms create their shells from carbonates, calcium carbonate to be specific. And so you might even see acids eroding statues and things that are made of marble, because marble's primarily made of calcium carbonate. And so whenever an acid is reacting with a carbonate, it's going to dissolve it to form carbon dioxide. This can happen very quickly in the volcano reaction, or it can happen very slowly over time in the sense of acid rain on a marble statue. And then acids and bases both, they when you dissolve them in water, they create an ionic solution. And so if it's an ionic solution, we can expect it to conduct electricity as well. And so aqueous solutions of acids conduct electricity. We can classify acids as being monoprotic or polyprotic. That's one level of classification. And then we could also classify them by the number of elements that are present. And so 2 or 3 elements present in the formula. So first, let's look at the monoprotic versus polyprotic. So what makes an acid is the fact that the formula it starts with a hydrogen ion. We know that ionic formulas always have a cation at the front and an anion at the back. The cation is typically a metal. But what's special about acids is that the cation is not a metal. Instead, it's hydrogen acting as a cation. And when it dissolves in solution, this cation hydrogen is what changes the properties of the solution. If you think about it, hydrogen as a cation. Okay, well, what's a cation? A cation is typically a metal, in this case hydrogen, where some of the electrons are not there, making it positively charged. Okay, well, think about it. Hydrogen, how many electrons does it have to begin with? It has 1 electron. So if it's a cation and it had 1 electron to start with, how many electrons does it have as a cation? None. Well, how many protons did it start with? 1. Neutrons? None. So a hydrogen ion is in fact a proton. Think about what a proton is. A proton is a very small, positively charged particle. And so when you put an acid in solution, it releases these small, positively charged particles called protons. And so when you have these protons, they are going to seek out and take electrons from anything that they can, because they're positive and they're desperately in need of anything negative. And that's what electrons are. They're negative. Well, think about what electrons do. Electrons make bonds. So if I have a substance that's all bonded together with all these electrons, and then I have some protons needing some electrons, well, guess what? Those protons will come in and take those electrons and rip apart those bonds. That's what allows acids to be corrosive. We know that acids dissolve things that you wouldn't expect it to dissolve, like metal. We could dissolve a piece of metal. That's crazy. The reason why is because it's literally a bunch of protons in solution and they're desperate for electrons. And so we could use the term monoprotic or polyprotic to describe how many protons actually end up in solution when the acid dissolves. Mono means 1. Protic means protons. So a monoprotic acid means that for every formula unit of the acid, we get 1 proton. Whereas polyprotic, poly means many or more than 1. So for every formula unit of the acid, we get more than 1 proton. Specifically, you could say instead of monoprotic, we could say diprotic or triprotic. Di meaning 2, tri meaning 3. So if you look at these example formulas, this first one, this is hydrochloric acid. By the way, we didn't learn acid nomenclature. If you need to know how to name an acid, you could look at your polyatomic ion sheet that I gave you earlier in the year, and it's at the bottom right-hand side of the sheet. You'll see a bunch of common acids with their names and formulas. Okay, going back. So hydrochloric acid, you could see that there's one hydrogen for every chlorine. So therefore, for one formula unit of this acid, it's going to give up one hydrogen ion or one proton. And so we call it a monoprotic acid because it has one proton per formula unit. The next one is HNO3. This is nitric acid. And so for every one formula unit of nitric acid, it gives up one proton. So therefore it is monoprotic. Over here in the polyprotic side, we have H3PO4. That is phosphoric acid. That's the soda that I previously spoke about being added to soda. That one has 3 hydrogens per formula unit. So therefore it is triprotic, tri meaning 3. The next one, H2SO4, that's sulfuric acid, also known as battery acid. That one you can see has 2 hydrogen ions. So therefore it is diprotic, di meaning 2. Generically, instead of saying di or triprotic, we could just say polyprotic, which means more than one. And so we have the di and the triprotic ones classified as polyprotic acids, and then we have the ones with one hydrogen ion, one proton, classified as monoprotic acids. We can also classify acids by the number of elements that are present. And so for an acid that is binary, there are 2 types of elements. So in these examples, I have hydrobromic acid. So I have hydrogen and bromine, so 1 element, 2 element. And then for the next one, I have hydrogen fluoride or hydrofluoric acid. And so therefore, that is just hydrogen's the first element, fluorine's the second element. So that is also binary. The last classification is ternary, ter meaning 3, like as in tertiary, primary, secondary, tertiary. Ter means 3 elements. And so these acids we'll find have 3 different elements. And so this first one, we have chloric acid, HClO3. So we have 1 hydrogen, 1 chlorine, or we have 3 types, hydrogen, chlorine, and oxygen. And so that is a ternary acid. And then the next one is sulfuric acid. So we have hydrogen, sulfur, and oxygen. Again, 3 elements. So those are ternary acids. These ones over here are binary. Now, these classifications happen simultaneously. In other words, if you look at this monoprotic corner up here of the slide, you could see that while these are monoprotic acids, if I look closely, this first one is a binary monoprotic acid because it has 2 elements and it's giving up 1 proton per formula unit. Whereas the next one has 3 elements, so it is a ternary monoprotic acid. Over here with the polyprotics, you can see both these have 3 elements, so they're both ternary acids. So we call them ternary polyprotic acids. These ones down here at the bottom left in the binary section, they're not only binary, but they're also monoprotic. So binary monoprotic acids. And then these ones at the bottom right, these are ternary monoprotic acids because they have 1 hydrogen and they have 3 elements. Okay, so we can classify acids based on how many protons they have, as well as how many elements are present. Here is a list of some common acids and their uses. Some of these might already be familiar to you. The first one is acetic acid. So acetic acid is an organic acid. We call it an organic acid because if you remember back to functional groups when we were studying a little bit of organic chemistry, you'll recall that a carboxylic acid or an organic acid functional group is one that has a carbon double bonded to an oxygen, and then it also has an alcohol group right off to the side. It doesn't show that in the formula here, but if you'd imagine this first oxygen being double bonded to the carbon, and then the hydroxide is then bonded to the carbon. So that is the carboxylic acid group. That's the organic acid group of the acetic acid. And so acetic acid is it's the main ingredient in vinegar. And so if I were to take this bottle of vinegar here, this is apple cider vinegar. And so This is not pure acetic acid. It's a dilute solution of acetic acid. So this is essentially apple juice, and it has acetic acid in it. So I don't know the exact process of how they do it, but maybe a fermentation process. But anyway, this bottle says that it's 5% acidic. Okay, and so it's going to be 5% acid, 95% water, and other components like apple juice in there. And so vinegar, the active ingredient is acetic acid. So it's kind of a misnomer to say that vinegar or acetic acid is vinegar. It's just that vinegar is a solution that contains acetic acid. We use it for food preservation and preparation. Obviously, not a very dangerous acid at that dilution level. However, if I were to have very concentrated acetic acid, so if I were to have like 95% acetic acid, that would be very corrosive, very dangerous to deal with. But in more dilute forms, like 5%, it's not harmful. We could put it on our French fries. The next one is acetylsalicylic acid. Acetylsalicylic acid is also known as aspirin. And so you've inevitably taken aspirin at some point in your life. And so we use aspirin for pain relief, fever relief, and to reduce inflammation. And so that is another organic acid. The next one is ascorbic acid, also known as vitamin C. We have previously learned that the two water-soluble vitamins B and C are needed. You need to take a lot of them because they're washed through your system. They're not stored in your fats. Ascorbic acid being the vitamin C, one of the water-soluble vitamins that you need. And then the other vitamins A, D, E, and K are all fat-soluble vitamins, and you don't have to take them as much. And you can actually take too much because they are stored in your body. They're stored in the fatty tissues. So ascorbic acid, again, that's an acid. Next one is carbonic acid. This is when we take carbon dioxide and we dissolve it in water to make it fizzy, a carbonated drink, if you will. That creates carbonic acid, which lowers the pH slightly. And so soda has carbonic acid. Also, water generally has a certain degree of carbon dioxide in it if it's exposed to carbon dioxide. And so there's concern that if we increase the carbon dioxide levels in the atmosphere through the combustion of fossil fuels, we will acidify our oceans slightly, enough such that calcifying organisms won't be able to form their shells properly. And we have seen evidence of this in the Arctic Ocean, where the water is very cold, so it's easier for carbon dioxide to dissolve, and therefore the water in the colder oceans is slightly more acidic. And some scientists have done studies to show that some of the smaller organisms, or like urchins in their nymphatic stage, when they're microscopic still, they have problems forming their calcifying exoskeletons, or their calcified calcium carbonate exoskeletons. And so that is a concern moving forward if we're going to continue releasing carbon dioxide into the atmosphere. The next one is hydrochloric acid. Hydrochloric acid, this is an acid that you have with you at all times. It is produced in the stomach, and it's used as an aid in digestion along with other enzymes, or along with enzymes like pepsin. And so the common name for this is muriatic acid. And so the hydrochloric acid in your stomach, it's not super concentrated, but it is concentrated enough that it is dissolving the lining of your stomach at all times. And the reason why you get a stomach ache is if your body is in a normal cycle of eating 2 or 3 times a day, it ramps up the production of hydrochloric acid in anticipation of having food to digest. If you suddenly miss a meal or it's late, your body might produce extra hydrochloric acid. Therefore, it's going to dissolve your stomach at a greater rate. That's why it hurts. But of course, our stomachs are constantly regenerating new cells. So that's not a huge issue. If you've ever puked, it's a terrible experience, but you might know that puke has a very sour taste. And the reason why is because it has an acid, hydrochloric acid. It's very important to brush your teeth after vomiting because it has acid in it. The next one is nitric acid. Nitric acid is an acid that you're probably never going to use or be exposed to at any point in your life, because nitric acid is a nasty acid. It is nitrogen trioxide dissolved in water. And nitrogen trioxide is a nasty gas. And so concentrated nitric acid will actually release this gas, and the nitrogen trioxide in itself is very corrosive. So when I store nitric acid at school, it has to be in a special cabinet. And even in that special cabinet, it corrodes the inside of the door, the hinges in the door, just from off-gassing. And it's a sealed bottle, mind you. It's just very nasty stuff to use. But it's used to make fertilizers. And so it's in this table because it's a common acid in that you eat food, right? Well, that food is farmed, and that food that's farmed needs fertilizer to grow. And so nitric acid is the acid that we use to produce that. The next one is phosphoric acid. Phosphoric acid, this is the acid that I mentioned is in soda. And I actually have a 2-liter bottle of Coke right here. And I'm going to read the ingredients. Carbonated water. So carbonated water, that's actually water with a little small fraction of carbonic acid. So the first ingredient is technically an acid. High fructose corn syrup, so the sugar. Caramel color. And then so they have more caramel color added to the soda than the next ingredient, which is phosphoric acid. And so we could see that the two main ingredients for sweetening Coca-Cola, because they list the ingredients in terms of how the prevalence, the two ingredients for flavor is the high fructose corn syrup for the sweetening, phosphoric acid for that slight sour taste, and then the last thing in terms of flavor is the natural flavors, caffeine being the last ingredient. And so phosphoric acid is an important component in sodas. Phosphoric acid has historically been used in detergents as well. It's very good for cleaning substances, so you can take stuff off glass. They used to put phosphoric acid in dishwashing detergent and other types of detergents for cleaning a whole myriad of things, and they worked great. And you could still get phosphoric acid based detergents. For example, if you work in a chemistry lab, the detergent that you use is probably going to have phosphoric acid in it to make it more effective. But phosphoric acid based detergents are no longer used for domestic use. You can order them special, but they're very expensive because they try to control how much is being used. Because what they found is that phosphoric acid is extremely bad for the environment, because phosphoric acid released into the environment it creates phosphate pollution. And as you learned 2 years ago in environmental science, phosphates and nitrates in surface waters is devastating. It causes eutrophication, causes algae growth, which depletes dissolved oxygen levels and causes die-offs. And so phosphoric acid, they try to limit its use, so therefore to preserve aquatic ecosystems. Slightly sour but pleasant taste, used in sodas. The last one is sulfuric acid. Sulfuric acid is known as battery acid. And so this is used in car batteries. In car batteries, it's a plastic enclosure, metal and plastic enclosure. It has sulfuric acid, and then it has these waffled panels of lead. And so the reaction between the lead and sulfuric acid is one that is electrochemical in nature, which provides electricity for starting your car. And the reason why we use chemical sulfuric acid batteries in cars rather than alkaline batteries is because a chemical battery made of sulfuric acid and lead is rechargeable over and over and over. And so as your car is driving, as the engine's running, the alternator is turning and charging the battery. And so you couldn't do that with an alkaline battery, which is your stereotypical battery. Lithium-ion batteries are a lithium polymer. As you know, the electric vehicle industry is taking off. So maybe chemical batteries are going to be a thing in the past in a decade or so, but time will tell. So sulfuric acid, very corrosive. Don't open those batteries up. So those are some common acids. Moving on to bases. Bases have the characteristic of being bitter. And so the reason why things are bitter, or we perceive them as being bitter, is because that's supposed to be a bad taste. For example, my coffee here, it has a bitter taste. And so That's actually one of the desirable things for coffee drinkers. A lot of people think it's the caffeine, which for a lot of people maybe it is, but people that drink black coffee, they probably drink it that way because they like the bitter taste. Why do you add sugar to coffee? Well, you're trying to eliminate that bitter taste, because bitter is typically not something that people enjoy. Some people do, but the majority of humans do not. And the reason why that is because humans evolved to avoid bitter things, and plants evolved to be more bitter, to not be eaten by mammals. And so it's a very strong indicator. If something is bitter, then there's a good chance it's going to be poisonous. However, as humans, we obviously exploit our environment, and we found some things that are bitter that aren't poisonous that we like. Chocolate, so the cocoa plant is very bitter. So if you think about dark chocolate, very bitter. Coffee, very bitter. So while bitter foods and drinks are very uncommon, because most things that are bitter are toxic, the ones that are palatable, there's a huge market for them. So bases have a bitter taste. And so if you ever put a base in your mouth, which I would never do that, I can't think of any base that's edible, but it would have a bitter taste. Bases are often found in cleaning products. Soap is a base. Ammonia is a common cleaning product. Household ammonia is I think it's a 10% solution of ammonia. Windex has ammonia in it. Those are all cleaning products, right? So bases, they're bitter tasting. They're found in cleaning products. The base that we use the most in chemistry is sodium hydroxide. That's the chemical name. The common name is lye. This is sold commercially, it was sold commercially as drain cleaner, called Drano, or Red Devil drain cleaner, but you can no longer get those very easily because it's very nasty stuff. It's very corrosive. So corrosive, it's going to dissolve the clogs in your drains, as shown in this image. But yeah, that's sodium hydroxide. Sodium hydroxide is straight up drain cleaner. Also, it's commercially available as oven cleaner. Sometimes it's available as an aerosol spray. So if you ever have drain cleaner or oven cleaner and you're unclogging a drain or cleaning your oven, it's very important you wear gloves, and definitely wear eye protection. Sodium hydroxide, if it gets in your eye, it's going to denature the proteins in your eye, and you're not going to see out of that eye again, probably. So very important. Whenever you're using a base as strong as sodium hydroxide or lye, you want to make sure you have your protective equipment on. So make sure you have it. The next characteristic of bases is that they feel slippery. Think about soap. Soap is very slippery. If I were to give you, so if I had two beakers, one's an acid, one's a base, and they're clear and colorless, you can't tell the difference visually. But if I were to put a drop of the base on your finger and you rub it between your fingers, it would feel very slippery. You might describe it as being slimy. That's a property of bases. So you can think about soap. Soap is slippery. Well, it's because it has a base in it. Next thing, indicators. We can use indicators to determine whether you have an acid or base. So remember how I just said that if you have two beakers, an acid and a base, they're both going to be clear and colorless. They're going to look like water. You're not going to, because you can't see dissolved substances. And so since acids and bases, they have properties that can be dangerous in terms of being corrosive, you don't want to just stick your finger in and see if it's slippery, right? And so we need ways of testing whether something's acidic or basic. And what we do is we use substances called indicators. They themselves, indicators, are very weak acids. But what's special about them is that they change color. So we have a visual detection of whether something is an acid or a base. And so on this slide, I have 3 different indicators that are commonly used in chemistry. The one at the top is phenolphthalein. If you don't want to write out phenolphthalein, you could just abbreviate it as pH. So you can see it starts with pH and has a pH right in the middle. Phenolphthalein is clear and colorless in acidic solution. So if I have an acid and I put a few drops of phenolphthalein indicator in there, it's going to stay clear and colorless. But if I put a few drops in a base, it's going to turn a magenta color very quickly. So we could use phenolphthalein to indicate whether we have an acid or base. This is kind of a more of a, you could see that the middle ground, it's kind of a faint pink, but there's not a much of a spectrum effect here. It's mostly, for the most part, either clear or magenta with very little in between. That's why we can have other ones like bromthymal blue at the bottom right, bromthymal. So BROMTHYMOL, bromthymal blue. You could abbreviate that one as BTB. You can see that this one, it has kind of a spectrum effect. And so when it is detecting for a base, it is that royal blue color. When it is detecting for an acid, it's kind of that yellowish gold color. When it's neutral, when it's neither acid nor base, it's going to be that murky green color. So that's a bromthymal blue. We can get a little bit more detection level with some indicators compared to others. The last indicator I've included is litmus. Excuse me. So litmus, it comes in two forms, red litmus and blue litmus. And we could determine whether we have an acid or base by using a strip of litmus paper. What litmus paper is it's just a piece of porous paper, like filter paper, cut into small strips and soaked in the chemical. And so if you have red litmus paper, you could test for base. Red litmus paper, if you dip it in the base, it will turn blue, just like the bromthymal turns blue in base. If you dip the red litmus paper in acid, nothing will happen. So it either is a base or it isn't. So it's a test that's either this or that. There's nowhere in between at all. If you want to test for an acid, you need the blue litmus paper. Dip the blue litmus paper in acid, turns red. If you dip it in the base, nothing happens. So blue litmus paper tests for acids, it'll turn red. Red litmus paper tests for bases, it'll turn blue. In pop culture, we use the term litmus test to describe anything that is a qualifying test of this or that. And so someone might say, well, the litmus test to determine whether you like this person would be, do they make you happy? Okay, well, yes or no. That obviously has nothing to do with chemistry, but you'll oftentimes hear that come up in a conversation, a litmus test. And so that has a chemical origin. It's actually a test for acids or bases. Moving on to the definitions of acids and bases, we have 4 definitions. We're going to be learning 2 of them. Just like anything else in science, science is a progression of knowledge. And so as we get more information, as we learn new things, we could advance our understanding. Well, acids and bases are no different. However, the more advanced definitions are kind of complex and more difficult to understand. So it is practical to learn the older ones because they are valid most of the time. And so the first definition of an acid base was developed by Svante Arrhenius in 1884. And he said, okay, I have these 2 solutions. They're not just normal salt solutions. They're special solutions in that they're corrosive. Acids and bases are both corrosive. So he said, okay, well, I know these are both corrosive, but they have different properties. This one's sour and this one's bitter. This one's slippery and this one's not. So he's like, well, I need to figure out exactly what I'm dealing with here. And so he came up with this working definition. He said, okay, if I put something in solution and I can test it and it tests positive for hydrogen ions, then it's an acid. So if you put something in solution, you dissolve it, produces hydrogen ions, we have an acid. And then for the bases, he said, okay, well, if I put the base in solution and I test it, it tests for hydroxide. So bases produce hydroxide when they dissolve. This OH is the hydroxide. And then acids produce the hydrogen ion when they dissolve. And that was his definition for the acids and bases. Very simple. Acids produce hydrogen ions. Bases produce hydroxide ions when they dissolve. And this works for most things. It works most of the time. But Johann Bronsted and Thomas Lowry short time later in the 20s, they said, well, wait a second, Arrhenius. There are things like ammonia, NH3. When we dissolve it, it doesn't produce hydroxide ions. There's no oxygen in ammonia. There's no hydroxide in ammonia to produce hydroxide ions. We know ammonia is a base. We clean all of our stuff with it. It's a cleaning product. It's bitter. Okay. They knew ammonia was a base, but it didn't produce hydroxide when it dissolved. So they said, well, wait a minute. Your definition isn't working all of the time. And so they revised the Arrhenius definition a little bit. For their purpose of the acid-base definition, they defined it in terms of whether something was accepting a hydrogen ion or whether it was donating or giving away a hydrogen ion. And so if you think about the Arrhenius definition of an acid, he said, okay, well, you dissolve it, it gives hydrogen ions. Okay, well, that's the same thing as the Bronsted-Lowry definition. It dissolves and it donates the hydrogen ions to something else. The hydrogen ions leave and it goes somewhere else. Johann Bronsted and Thomas Lowry said that. Arrhenius said that. So the acid definition is one and the same. Where the definitions differ is with the base. Arrhenius said, okay, you put a base in solution, it produces hydroxide. Well, these guys said, well, that, not all bases have hydroxide. So instead, a base is something that accepts a hydrogen ion, meaning they're not giving hydrogen ions, they're receiving them, they're accepting them. Well, let's think about that. Hydroxide is an anion. It's extra negative. Hydrogen ions, they are straight up protons. Doesn't get more positive than that. So is it so much of a stretch to say that a hydroxide ion, super negative, would easily accept a positively charged hydrogen ion, a proton? Yeah, it would. So a hydroxide ion is a hydrogen ion acceptor. So we're assimilating Arrhenius' definition into this new definition. And then now this new definition works for everything. And so they just said, okay, bases, they're negatively charged species that accept hydrogen ions. That's it. Simply put, acids and bases are things that dissolve in solution. Acids form a positively charged solution. Bases form a negatively charged solution. And because of that charge difference, they react differently. One of the outstanding characteristics of both is that they can be corrosive. It was also discovered that hydrogen ions don't actually exist by themselves in the solution, which makes sense. Protons, those subatomic particles, positively charged, how could they ever just be floating around? They have to attach to something negative, anything negative. Well, water has some free electrons on the oxygen. So when you put an acid in solution and those hydrogen ions, those protons break off, they just attach on, they cling on to water molecules. And so hydrogen ions, they don't exist freely. They exist in this complex called hydronium. And you can see this is the formula for it, H3O plus. So it's just water plus an extra hydrogen, H3O, as opposed to H2O. And then obviously it's positively charged because it has an extra proton. So here are some examples of Bronsted-Lowry acids and bases, and we can kind of analyze these. So here's a generic example up here. We have the substance and we're putting it in water. When we do that, water becomes hydronium. So it took on a hydrogen ion, it accepted it. So therefore water, in this case, is acting as a base because it's accepting the hydrogen ion. And then this generic acid, HA is obviously not an element, it's just a generic formula. This, from here, from the reactant side to the product side, it loses the hydrogen. Well, where did it lose it to? Well, it gave it away to the water. So this is the hydrogen ion donor, the acid, and water is the hydrogen ion acceptor, the base. So we have an acid and a base reacting to form hydronium and another, we call it a conjugate. So here's a specific example. We have hydrochloric acid, obviously an acid. It has acid right in the name. It donates its hydrogen to the water. Water becomes hydronium. So hydrochloric acid is the hydrogen ion donor, the acid, and water is the hydrogen ion acceptor, the base. So water is functioning as a base in these two up here. Down here, we have the generic formula for a base, and we see from left to right, this loses a hydrogen ion. So if it loses a hydrogen ion, actually, this isn't the generic formula for a base. I'm sorry. It's just the next letter. The B threw me off. So this is giving away a hydrogen ion, just like the hydrochloric acid did up here. So from left to right, it loses a hydrogen ion. Well, where did it lose it to? It lost it to the water. The water accepted it. So water is a base. And then this is the acid. So in this top one, the hydrogen is the cation, and this bottom one, the hydrogen is the anion. And then this last example, we have ammonia, a known base. Ammonia, from left to right, it goes from 3 hydrogens to 4 hydrogens. Ammonia is gaining a hydrogen in this case. So in this instance, this is the base. The ammonia is the base because it's accepting or receiving the hydrogen ion. And the water goes from this to this. It goes to hydroxide. Well, there's our hydroxide showing up for the Arrhenius definition. So water is losing a hydrogen ion. So if it's losing a hydrogen ion, it must be giving it away or donating it somewhere else. Well, where is it donating it to? It's donating it to ammonia, the base. So in this case, water is functioning as an acid. Well, up here, water is functioning as a base. Down here, water is functioning as an acid. Water is special. Water is what we call amphoteric. Amphoteric means it has dual qualities, or amph, the prefix amph means it has dual qualities. Think about amphibians. Amphibians can be aquatic organisms, and they can also be terrestrial organisms. Well, they're actually terrestrial organisms that live part of their life in the early stages of their life in aquatic ecosystems. So they're amphibians. They have dual qualities. Amphoteric we can use to describe water. So it can act as a base, or it can act as an acid. It just depends on what it's being combined with. So water is amphoteric. That's it. So that's all. There are 2 other definitions of acids and bases. They are most often used in organic chemistry, and they are beyond the scope of this course. So next, we want to work on our science notebook. So we're going to complete our science notebook. And what's not finished needs to be finished for homework. And then there is a review. And I already talked about that at the top of class. So go ahead and I'm going to post that. And you can get started with that and work